Okay, so here's a form of energy that I'm always excited about. It's called geothermal energy. And it's something that we've known about for a long time, used a little bit, but I think in the future it probably has the potential to become more widely used. So let's just learn about how geothermal energy works. So remember that this is not solar based. Okay, so this has nothing to do with the sun for a change, like nuclear power. Basically, the Earth's interior is hot because radioactive decay is happening in the core of the Earth, where all these heavy isotopes have accumulated, and every time they undergo radiation, they give off heat energy. This heat radiates out from the center of the Earth outwards, and so when we get near the surface where we can interact with this heat energy, we can sometimes use it to help us with our energy needs. So the two main ways we use it are we can uh, create steam pressure, which can then turn a turbine to make electricity, just like we do with coal or nuclear, or we can simply use it as a way of uh, reducing our needs to heat and cool by simply letting the world do it for us using the internal heat. It's a little bit harder to understand the second one, but I'll explain as we go on. Okay, so let's just talk about how we generate electricity, because that's the main thing you're expected to know here. So basically, there's three different ways of doing it. We have what we call dry steam, flash steam, or binary cycle, and they're all really cool. I'm excited about all of them. And basically, it goes like this. This is used where you have basically the hottest environment. This is a medium hot environment, and this is a little bit of a almost too cool to ordinarily work, but they found a way of making it work. So let's just go on. So dry steam plants basically they only work in a very few places where you have basically a magma body that's really close to the surface, and basically what happens is there's just pressurized steam that's down underground naturally. Just groundwater gets in that magma body and it turns into steam, and you just have to drill a pipe down into it, and that up comes steam constantly, and you just blow it over a turbine and you make electricity. And so um, there's just not a lot of places where you can do this. For instance, like they can do this in Iceland. In the United States, the world's largest geothermal facility is in California, a place called the Geysers. It's near Mount Lassen. And it's, like I said, the world's largest geothermal facility. The United States could do it in Yellowstone. I heard an engineer from Iceland going, hey, the United States could have like all the electricity they'll ever need forever if they just convert Yellowstone into a power generating facility. But it's too nice. We're not going to do that. Okay. Uh, but there's really not a lot of places where you can do it just because it requires a very unusual thing, a large magma body close to the Earth's surface. But let's just see how it works. All that you do is you drill this pipe down, pressurized steam comes out of the ground, it hits this turbine, spins the turbine, turns the generator, makes electricity, and then as it does this, the water cools off. We just pump it back and we call it an injection well, because even though it's cooled down, it's still really hot. And what we don't want to do is we don't want to cause the rock down below us to end up becoming depleted in water or in temperature. Okay, so and interestingly, the first one was kind of near Mount Etna in Italy, and that was over 100 years ago, and it's been operational ever since. Now, flash steam is more common. Okay, so this is how it is usually done. Okay, so flash steam can be done in a lot more places, and basically it involves bringing up water that's still liquid, at least as we're bringing it up, but it's superheated, but it's under pressure. It's like 182 degrees Celsius. So normally it would start boiling at 100 at atmospheric pressure, but at high pressure inside the Earth, it's still a superheated liquid. But as it rises and the pressure drops, then what happens is it will flash into steam, and so we'll get a separation of steam and liquid water. And so we take the steam component of it and we turn a turbine, and then we put the hot liquid back into the ground. Now, the reason they're more common is you can have deeper magma bodies. They don't have to be quite as close to the surface, and there's a lot more of those out there. And many of them are being developed as we speak. Uh, and so here you go. So we have this was water is being brought up from below. Now this water is superheated, but it's still liquid. And now what happens? It gets into here and we flash it. We drop the pressure so that the steam comes up and turns the turbine, but a lot of it stays as liquid water and comes here, and then the liquid component goes here, the steam component gets condensed and comes in here, and again we inject it in there because we don't want to cool off the rock down below. So it's very similar. The only difference is that what's coming up isn't just steam, what we call dry steam. It's water that then flashes into steam as the pressure drops. Now, the coolest one, I think, and the one that's going to become more prevalent as time goes by, is called the binary cycle geothermal plants. And these are kind of new, and so there's not a lot of them, but they're very promising and very awesome. So the idea is, if the water is cold enough that it is still is below that 182 degrees Celsius, it's over 100, but it's not hot enough to make pressurized steam that can turn a turbine. Don't worry. Here's an idea. Some great person said, well, who says we have to use water to turn a turbine? Couldn't we use some other pressure? Like, does it have to be steam? And no, it could be anything. So a lot of petroleum compounds are liquids under small pressure, but then they turn into gases. They have a very low boiling point. Same thing's true for ammonia. So we could use these, what we call a working fluid, that we're going to boil those with hot water. All right, and then I'll show you how this works, because it's a really cool thing. The nice thing about this is it doesn't require nearly as high temperatures, and therefore the places in the world where this can be used are much more common. So watch this. All right, we bring up this hot water, say between 108 and 180 degrees Celsius. Not hot enough to turn our turbine. But what happens is it's going to pass through. It's sort of simplified here to actually go through a heat exchanger. But as it goes through here, this is our working liquid. This could be ammonia. This could be butane, whatever. But it's going to be boiled as a result of being heated by this. So it turns into vapor under pressure, turns the turbine, which then comes back into here, and we just keep the process going. It's a little more complicated because we have to have a condenser to do this. But the bottom line is there's two loops. There's the hot water loop coming up from down below and back down. So that's just groundwater that's really hot. And then there's this other loop here, which is the working fluid, which is actually vaporizing and turning the turbine. Pretty cool, huh? Man, whoever thought that was having a great day. Now, there's places where the rock is hot but dry. Okay, so there's no steam coming up. Well, darn, what do you do? Well, now hang on. Remember we talked about fracking? So people thought, well, you could use this fracking technology to do this. So basically, the same technology used for fracking to get natural gas would work for this. You basically pressurize this rock, this dry rock, and you fracture it. Then you have an injection well which pushes cold water down, which seeps through these hot fractured rock crevices, turns into steam, comes up, turns our generator, just like it would if it was like a dry steam plant. So it's basically we're making dry steam where we didn't have steam to begin with, pumping it back down and creating a cycle here. So it's not as efficient because we got to pump the water back down under pressure. So it doesn't produce as much usable. I mean, basically, when you look at your energy expenditure versus energy output, it's not as good, right? But it still would work. Now there's a couple of worries. One is these are the same worries that we have with any kind of fracking technology, and the one is that you have the potential to contaminate aquifers because you're pumping. It's not just water you're pumping down. There's other things in it to help it do its job. And the other thing is it can trigger earthquake, which, by the way, here in Korea, and I remember I felt this earthquake back in 2017. I was up on the G building, 6th floor during my planning period. And all of a sudden, and this is when we were having a lot of tensions with North Korea. And all of a sudden I felt that the whole building do this. And my phone went, I'm like, oh my God, I think we just got nuked. My heart was just thumping. And I looked at my phone and it's in Korean, so I don't really understand what it says. But I saw 5.2 and I'm like, 5.2 sounds like a Richter magnitude. It's an earthquake, and that's what it was. All right, didn't get any more. Okay, Korea is not on a plate boundary. We don't usually get earthquakes, but you still sometimes get earthquakes when you're not on a plate boundary. Turns out, I just learned recently, it was because Korea was developing one of these fractured rock injection well hydrothermal plants, I think down near Pohang maybe. And in the process of doing that, they triggered an earthquake. I don't know. I haven't read a lot about it, but they probably stopped the project after that. So that is one of the drawbacks to this. It is a potential clean energy source, but it does have that drawback that the same as fracking does. Okay, let's just talk about the benefits and drawbacks of geothermal. So the benefits, it's renewable for the most part. So in most places, the heat of the earth is never going to cool down. I mean, humans will either go extinct or evolve into something else long before the world runs out of heat. The world's going to last a long time, okay? Uh, but the thing is, in some places the rock cools down, so that may not work, okay? But it's essentially renewable. And it doesn't involve fossil fuels, so it doesn't generate much in the way of carbon dioxide. It has what we call a small footprint. You don't have to have a lot of space to make this happen. And it also has the benefit that, unlike other things we'll talk about, like wind energy and solar energy, it's constant. Day, night, winter, summer, it's always putting out a known amount of kilowatt hours. So you can count on it. It's reliable. It makes for a stable grid. Now, some of the problems with it is the biggest one is you just can't do it in the vast majority of places in the world. Okay. Even if you use the binary method, it's still there's just not a lot of places where the groundwater comes up over 100 degrees. All right, now, the other thing is it can also bring up some things that are natural gases in the earth. So it can bring up things like sulfur dioxide, carbon dioxide, methane. So it can bring up gases, and some of these are ones that cause acid rain. Some of these are ones that cause global warming. But keep in mind, they bring up at a much, much less rate than what you would get from burning coal. It's still infinitely better than burning coal. Now, in some places, the source rock, places where we've been doing this, like Klamath Falls, Oregon, where we've been doing this for a while, over time the rock cools down, and so the power output is dropped by almost 50%. So that's not good. Okay, that's something that has to be figured out. These are not cheap. So, like nuclear power, the initial costs are quite high. Although over time, when you scale over the lifetime of the plant, the electricity is cheaper than coal. It's just a lot more expensive to build that initial plant. And in addition to bringing up carbon dioxide and sulfur dioxide, you can also end up bringing up heavy metals because that's where they come from down below. So you could potentially contaminate water supplies this way. All right, nothing's ever easy. Okay, now this is kind of interesting graph here. Okay, so look at this. This side here is the world's leading. Now this is a little bit old, right? 2013, but still, let's just go. Okay, the world's leading generators of hydrothermal electricity. The United States. Ooh, look at that! Go USA! Philippines, Indonesia, Italy, New Zealand, Mexico, Iceland's way down here, right? All right, and so on. Now, what do all these have in common? They're all on plate boundaries, right? They're all in places where you have subduction and you have melting and you have magma bodies near the surface. Every single one of these is on a plate boundary of some kind. Iceland happens to be on a mid-ocean ridge, but the rest of them are basically at convergent plate boundaries. Now look over here. The share of electricity that's generated by it. Well, Iceland, even though it's way down here, it only makes like 700 gigawatts. 700 I was like 700 megawatts, that turns out to be a significant portion of their overall energy needs. Same thing's true for El Salvador, Kenya, Philippines, Costa Rica, New Zealand. All of them is a significant portion, even though they really aren't making that much. The United States, we don't even rate here because we have such huge energy needs over there that even though we produce the most of it, we need a lot of it. Okay, but Iceland's kind of an interesting one, right? Because they don't have to generate that much, but not that many people live in Iceland, so a third of their energy needs are coming from that. So here's a map, basically. If I said, "What is this a map of?" I mean, I would just look and say, it looks like an earthquake map or a volcano map, which is essentially what it is, right? It's a plate boundary map, but this is actually a map of where geothermal potential actually exists. So the darker it is, the closer the magma is to the surface, and the more likely you are to be able to use flash steam. And then there's other places where you could use binary systems. The last thing I want to talk about is this: heat pumps. Heat pumps are cool. Heat pumps is a form of geothermal energy that's used all over the world. My sister has one. All right, so they're very common. So the idea is everywhere in the world. If you dig down, it's warmer than it is at the surface, at least in the wintertime. All right. So the bottom line is, if you go down, say 10 meters, it's a constant temperature down there, right? So you go down a few meters, and the temperature is about 10 degrees Celsius. Summer or winter, I don't care where you are in the world. If you go down, not that deep, the temperature is a pretty constant. If you've ever been in a cave, no matter where you go in the world, you go into a cave, it's about 10 degrees C, right? Well, the idea is, if I pump water down there, it will end up at 10 degrees C as it moves through a loop in the ground. Okay, and that's pretty cool because in the wintertime, the air here is below 10 degrees Celsius. So I want to heat my house up. So instead of just bringing in air and trying to heat up that, instead what I do is I pump water down into the ground, and it's going to heat up to 10 degrees. So when it comes up, that 10 degrees gives me an energy efficiency. So, just by by the little bit of energy it took to move water through this cycle, I was able to pick up some heat energy, bring it into my house, and it increased the efficiency with which my heater works. Right, is getting that added benefit of already having started from a warmer standpoint. But then in the summertime, the opposite is true, right? So in the summertime, it's more than 10 degrees outside. Man, it's 40 degrees outside. Well, guess what? Down here it's 10 degrees. So I pump water down here, and the water in my house cools down to 10 degrees. In the wintertime, it heated up to 10 degrees. In the summertime, it cools down to 10 degrees. So now my air conditioning system isn't having to work as hard. So it's not like I'm generating electricity with this, but what I'm doing is I'm tremendously increasing the efficiency of my heating and cooling, which is a big part of the energy demands, at least from the residential perspective. And so it costs a lot of money. My sister paid close to $7,000 to put hers in, so that's why a lot of people don't do it. However, once you put it in there, it's going to last you pretty much forever, and it reduces your heating and cooling needs by about 50%. All right, and that's pretty depending on where you are, right? But up to 50%, which is really significant. If everybody did this, imagine if we reduced that energy demand in the world by 50%, that would really help. So this is something that's not as glitzy as like binary, geothermal plant. However, it's something that everyone can do, and if the government helped everybody put it in, it would really help out. All right, sorry this one took so long. I got excited about it.